All right, so we've talked about ionic bonds, we've talked about covalent bonds, we've talked about those intermolecular forces between the covalent molecules. So now let's talk about metals. Okay, let's say you have a sample of nickel, you have a copper penny, you've got, a piece of aluminum foil. What makes metals metals? Why do they have high melting points and high boiling points? What makes them malleable? Why are they highly conductive as solids? And the reason is because of the way these metallics are structured together and how those atoms come together and bond together in a metallic bond. Now, these metallic forces are actually pretty strong. They're stronger than the forces that hold together covalent substances. And remember, the forces that hold together those covalent substances are hydrogen bonds, dipole-dipole interactions, and London dispersion forces. They are strong. Metallic bonds are stronger than those three things. They're not quite as strong as an ionic bond, but they are stronger than covalent bonds, okay? So the way this works is that it forms what we call a sea of electrons. And so we have all of these positive nuclei because, as we remember, all metals are losers. They're losers. They're going to lose all of their valence electrons. And so essentially what happens when you have a sample of a metal is that you have all of these positive nuclei surrounded by this electron cloud of moving valence electrons that actually go between all of these nearby positive nuclei. And as these electrons are moving around these positive nuclei, it holds those nuclei of those metallic atoms together into this really strong metallic structure. So we call that a sea of electrons. Now this sea is formed from what we say delocalized electrons. They don't really belong anymore to just one nucleus or another nucleus. They go back around through the sea between all of these nuclei, joining those together. So they're delocalized. They don't belong to one place or another place. This is a strong intramolecular force. Remember, intramolecular forces are bonds. They're bonds. Ionic bond is a strong intramolecular force. A metallic bond is also a strong intramolecular force. Polar and non-polar covalent bonds are weaker intramolecular forces. Hydrogen bonds, London dispersion forces, and dipole-dipole interactions are not intramolecular forces, they are intermolecular forces, okay? Anyways, metallic, that's what we're talking about here in this video. Metallic bonds, they're stronger than those covalent bonds, they're not as strong as ionic bonds, and it's formed from these delocalized moving electrons. So let's take a look here. Look at this data. We can see the melting points and boiling points for sodium, magnesium, and aluminum. What do you see in the data? What's happening to that melting point as you go from sodium to magnesium to aluminum? What's happening to the boiling point as we look from sodium to magnesium to aluminum? They're getting higher. Sodium has the smallest, the lowest, I should say, and aluminum has the highest. Well, why is that? Why does aluminum have a higher melting point or boiling point? Why does it take more energy to get that to melt or to get it to boil? And that's because aluminum has more valence electrons. So that means it has more delocalized electrons swimming in that sea, joining those nearby nuclei together. When we have more delocalized electrons, that means that we're going to have a stronger metallic bond because we have more electrons joining those nuclei together. When you have a stronger bond, it takes more energy, so a higher melting point and a higher boiling point, in order to get those phase changes to occur because you have a stronger bond to break, okay? So let's practice. Let's take a look at this question here. Which element consists of a positive ions immersed in a sea of electrons? Anytime you see sea of electrons, that tells us that we're talking about a metallic bond. Now, don't get yourself confused. Yes, letter D, Cu. That's a metal, but that's not a metallic bond because CuO is an ionic compound. So the only one that has a sea of electrons is the solid copper, letter C. Which of the following would exhibit the strongest metallic bond? So looking at our answer choices here, we know it has to be between which two? It has to be between A and B because the other two are not metallic bonds. So between lithium and calcium, which one's going to have a stronger metallic bond? Remember, it's going to be whichever one has more delocalized electrons. That's going to be letter B. And then lastly, which of the following would exhibit the strongest intramolecular force and the weakest intramolecular force? So it's asking for intramolecular forces, so we want to compare ionics, metallics, and covalents. So lithium is metallic. Calcium is metallic. AlCl3 is ionic because it's a metal and a nonmetal. H2O is covalent because it's two nonmetals. So that means the strongest is going to be AlCl3 because ionics are the strongest intramolecular force. The weakest is going to be the water because covalents are the weakest intramolecular force. Okay? So if you have any questions about how to determine between ionic, covalent, and metallic, which one's strongest, which one's weakest, just let me know. All right, I'll be happy to help. Thanks, guys.